Now let's see this question. The balloon, light rope and the monkey shown in figure are at rest in the air. If the monkey reaches the top of the rope, by what distance does balloon descend? Mass of the balloon is m, mass of the monkey is small m, and length of the rope ascended by the monkey is capital L. This is the case. This is the balloon. This is balloon, and my drawing is very poor, so I'll call this monkey. This is monkey. This is monkey, and this is the string, right? The question says they are at rest. They are at rest. Why they are at rest? You have a force mg plus a small mg acting vertically downward direction. So what keeps this system at rest? It's not a part of question. I'm just asking just for the sake of knowledge. See, when this forces, you have gravitational force capital mg, small mg acting downward direction. So why the question say they are at rest? Which force keeps them at rest? It is a buoyant force. Balloon must be containing a gas lighter than air. Balloon must contain, if you want the whole system to be at rest, balloon must contain a gas lighter than air. What is the molecular mass of air? Roughly, you have 78% nitrogen. So let's say I round off, let's say 80% nitrogen, sorry, percentage, 80% nitrogen, 78%, but I just want a rough calculation, and say 20% oxygen. So nitrogen has got molecular mass 28 and oxygen has got molecular mass 32. So 28 into 4, 32 into 1 upon 5. So it should be how much? It should be near about 29 grams. So you must fill this balloon with either say H2, which has molecular mass 2, or neon, which will be 20. So you can fill with these gases. In that case, there will be a buoyant force acting in this direction, which will be equal to the difference of the weight of the air in this and H2 in this. The weight of air, if suppose the balloon would have been filled by air, what is the weight? If balloon is filled by H2, what is the weight? Difference of it will be the buoyant force, Fb, and this must have been balancing this mg and a small mg. Only then the balloon can come at rest, right? So this is how the balloon might be at rest. That may be the physical reason why the balloon is remaining at rest, right? Okay, let's come to our problem. Let's come to our problem. Problem is, okay. So this is at rest. Let's assume it is at rest. It is at rest. It is in equilibrium. It is in equilibrium. There is no external force acting on this. The net external force acting on the system of balloon plus monkey is 0. Net external force acting on the system of balloon plus monkey is 0. That is what I mean to say. Net external force acting on the balloon plus monkey is 0. Now it says, by what distance balloon should descend if monkey reaches this position? If monkey reaches the top of the rope, this is top of the rope, by what distance monkey should descend? Again, same thing, the law of averages. If y position of one particle is increasing, in order to keep average same, your y position of the other body must decrease. And why YCM is same? Because you don't have any external force in y direction. So Fy ext is 0. It means ACMY is 0. When ACMY is 0, VCMY is constant, and then I can say initially the velocity of monkey as well as balloon was 0, so I can say VCMY is also 0. So when VCMY is 0 at t equal to 0, it will always remain 0 because VCMY has to remain constant. So YCM has to remain constant. YCM has to remain constant. Okay, So when YCM has to remain constant, if Y position of one body is increasing, the Y position of the body must decrease in order to make this constant, in order to maintain YCM constant. If Y position of one body is increasing, the Y position of other body must be falling. Getting a point or not? So let's calculate YCM initially, and say, first of all, in order to calculate YCM, let's take a reference for measuring Y position. Let's take some horizontal line which can be used as a reference for measuring Y, which can be taken as, let's take some horizontal line which can be taken as a reference for measuring Y position of the balloon and the monkey. Say this is the reference position. Let's say it is this. You can take any reference. There is no hard and fast rule. So I am taking this as the reference, right? Suppose here lies the center of mass of balloon, and say the monkey is, here is the monkey, here is the center of mass of monkey. It should be here, just for the sake of, or if you wish, you can take, center of mass monkey over here. So let's say center of mass of the monkey is here, right? Now say this is at a distance of y1, set a distance of y1, and say this is at a distance of, say, y2. So I'll write YCM as, I'll take YCM as, if I take this direction as positive, then YCM initially was m into y1 plus small m into, say, y2. Suppose this balloon is having a dimension, say the balloon is having a dimension of h1, and say the distance of the center of mass and one end of the rope of the monkey is, say, h2. So I can say this is h1 plus L plus h2 upon m plus m, right? Now when the monkey is ascending, monkey ascends, see this is h2 is distance between center of mass of the monkey and the other end of rope, the end of the rope which monkey is holding, right? Now when the monkey is ascending up, monkey is climbing up, the balloon must descend in order to keep YCM same. So I'll draw the final position when monkey ascends to this rope. Suppose the balloon descends by a distance of y. Suppose monkey, when reaches at this knot at the end of the rope, then suppose the balloon descends by a distance of y. Let me draw the figure. Suppose the balloon descends by a distance of, say, y, right? This is the center mass of balloon. The monkey is here. The monkey is here. So this is same as h2, and this length is going to be h1. Okay, and this is, say, y1. So your final center of mass YCM is going to be mass of balloon into y plus y1. And where is the monkey? Monkey is m y plus h1 plus h2, h1 plus h2. I hope I am correct. Yeah, I will be correct. So this is m. So if I just equate the center of mass, the y component of the center of mass should not change. So this means my1 and mh1 ml plus mh2 my my1, my, mh1 and mh2 should be equal. So this will cancel out. This will cancel out. So your y is going to be ml upon m plus m. So y is going to be ml upon m plus m. So balloon will descend by this magnitude. Balloon is going to descend by this amount, right? And going to descend by this y distance. Okay. So that's how we can use center of mass, the concept of center of mass, to solve this problem. I'll go for the next question. See this question. A man of mass m having a bag of mass small m slips from the roof of the tall building of height h. He is slipping from the roof of the building. This is a building of height h. He is slipping from the roof of the building of height h and start falling vertically. Initially the velocity was 0 and they start falling vertically, right? When he is at height h, when at height h from the ground, when he is at a height h from the ground, this is the ground. He notices that the ground below him is pretty hard. This ground is hard, but there is a pond at a horizontal distance x from the line of fall. There is a pond at a distance of x from the line of fall. Okay. In order to save himself, he throws the bag. He is carrying a bag also. Let's say this is the bag. He is carrying a bag. He is carrying a bag also. He throws the bag horizontally with respect to himself in direction opposite to the pond. He is throwing the bag like this, right? He is throwing the bag in this way. He throws the bag horizontally. He imparts a horizontal velocity to the bag, so it will undergo a projectile motion. The bag will undergo a projectile motion. He throws the bag horizontally with respect to himself in direction opposite the pond. Find the minimum horizontal velocity imparted to the bag. What should the minimum horizontal velocity v imparted to the bag so that man lands in water? What velocity v he should impart to the bag so that he lands in water, right? So that he lands in water. Pond. Calculate the minimum horizontal velocity imparted to the bag so that he lands in water. If he succeeds, he just succeeds, means he just provides enough velocity so that he just be it over here. He provides the minimum velocity so that he can be just over here. So just succeed means he is falling at this position. He just succeed to avoid the hard ground. Where will the bag land? When he is falling over here, where is this bag landing? We have to find x dash, you can say x dash. We have to find x dash. First of all, what should the minimum velocity imparted to the bag, right? He is throwing the bag horizontally, in horizontal direction. So when he is throwing the bag in horizontal direction, then from law of conservation of linear momentum, see, if I consider bag plus man as a system, then on the bag plus man as a system, there is no external force acting in x direction. If I take it as x and y, there is no external force acting on the bag plus man as system in x direction. Whatever force man is applying on the bag and bag is applying on the man is an internal force. So you can say the linear momentum of bag plus man plus bag must be conserved. Linear momentum initially was 0. Suppose the man throws the bag with velocity v, and as a result, say the man gets thrown in backward direction. Man gets a recoil with a velocity of v dash. It means initial velocity was 0. The final velocity is going to be mv dash minus mv. mv dash minus mv. This is the linear momentum after throwing the bags. This also must be equal to initial momentum, that is 0. So v dash which you get is mv by capital M. Is it not? mv by capital M. Now he has to land in water. He has to land in water. What is x? What will be x equal to? X will be equal to V dash into time taken by man to fall a distance of h, small h. V dash x is going to be velocity v dash into time taken by the man to fall a distance of h. See, when man is here, he has already attained some velocity. He is falling from this height. Here it was velocity was 0. Then he has come to this position. By the time he falls to this position, he must have gained some velocity. He has fallen by a distance of h minus small h. In that process, he must have attained some velocity in vertical direction, in vertically downward direction. So what should be the time taken by the man to travel distance of small h? See, in the whole process, the vertical component of the motion is undisturbed. The vertical component of the motion is remaining undisturbed. So you just tell me what time man takes to travel this distance. This must be equal to t1 equals to under root twice of h minus h by g, 2h by g. This is the time taken by the man to fall this distance h minus h. And now tell me what time the man will take to fall from this position to the ground. That will be equal to t2 to h by g. So now you tell me what is the time taken by man to travel this smallest distance. That should be equal to simply t should be equal to under root 2h by g minus. This is because the vertical motion remaining unaffected. It's only horizontal motion is created. Vertical motion is not changing. You don't have any force acting. You have only the force, gravitational force acting in vertical direction. So the vertical trajectory, vertical motion is remaining unaffected. So this is v dash t, and this is the horizontal distance traveled. If I don't call it x, I call it horizontal distance traveled. Horizontal distance traveled by man, and this must be equal to or greater than x. That means what is v dash? V dash is your mv by m and 2h by g must be greater than x, greater than equal to x. So v must be greater than equal to m by mx this should be okay. So the minimum velocity which must be imparted to the bag is going to be mx upon m 2h by g and this is the minimum velocity which must be imparted to the bag so that the man is safe, right? So that the man is safe. Okay, now the question says if the man just succeed to avoid the hard ground, it means the man is given this velocity only, so that he has just succeeded. Now question says where should the bag land? See, again I'll tell you that initially bag and man was together, so center of mass was over here. Now when man is throwing the bag on the system, still the net force, a net external force on the system is, earlier also it was m plus mg and now also it is m plus mg. So there is no reason why center of mass should change the trajectory. Center of mass was moving along this, so center of mass should continue to move along this, because whatever man and bag are doing, they are not creating any external force. There is no external force is only m plus mg. So the center of mass should continue with its own trajectory and the center of mass should fall over here. Center of mass should fall over here. The man is here, the bag is here. Center of mass is this. So in that case, if I take this as the reference, then center of mass is at a distance of x, man is at a distance of 0, and the bag, where is the bag? Here is the bag. M will be over here. So that will give me x dash. I want x dash basically. From where I have to calculate the distance of succeed. Where will the bag land? We have to find x dash. So mx plus mx is mx plus mx dash. This will cancel out, and x dash would be mx by m. So here is the bag. Bag should be at a distance of x dash from this center of mass. Alright. So this is your answer. This is your answer. But my dear friend, I don't think when we are falling from some height we are able to apply so much of mind. I think it takes just seconds to fall such a height. So this physics, I don't know, I have never tried it, and you don't try it also. Okay, so let's go to next question. This is your question. A block of mass m is free to slide on a frictionless floor. The block has a cylindrical cavity of radius r. This is a cylindrical cavity of radius capital R. In the middle of it, the center of mass of the block lies on the dashed line. Center of mass of the block is here. Okay. Through the center of cavity. To the center of cavity. This is center of cavity. Initially, center of mass of the block is at a horizontal distance x1 from the origin. Center of mass of the block is x1 from the origin. Now the point particle of mass m, this is point particle of mass small m, this is mass capital M, is released from point O, it is released from point A into the cavity. There is negligible friction between particle and cavity surface. When the particle reaches B, when the particle reaches this position, which is B, the center of the mass, center of mass of the block is at distance x2. Find x2 minus x1. Okay, good question. See, here also, if I consider the block and particle, this big block and the particle as a system, then there is no external force in x direction. It means ACMX is 0. The only force you have is mg, capital Mg plus small mg, and that is in y direction. That is there in y direction. There is no external force in x direction. They are exerting a force on each other, but that is internal force. So ACMX is 0. ACMX is 0. It means VCMX should be constant, and initially we are knowing they are not having any velocity, so VCMX is 0, so it should always remain 0 forever. VCMX at t equal to 0, so it should always remain 0. It means XCM is constant. XCM is constant. And what was XCM in the beginning? Can you tell me? This is small m. What is the distance of this small m from y-axis? It will be x1 minus this r. Small m, x1 minus r. And wedge is the distance of x1 m. Now, when this particle reaches this position, when the particle reaches this position, now your particle is here, B. This becomes x2. So finally your center of mass will be, small m will be at x2 plus r plus the block is at x2 m plus m. Okay, so what we have to find is x2 minus x1. Okay, so this will cancel out and we have mx1 minus mr, mx1 and mx2 plus mr plus mx2. It means this is going to be 2mr m plus m x2 minus x1, or there's 2mr upon m plus m. So that is x2 minus x1. Means if the particle is going to B, the block must move in this direction, and that's quite true. That's a law of average. Say then one particle, the exposition of one particle is increasing, the exposition of the particle must fall in order to keep your average same. Okay, so these are the questions on center of mass. Okay, thank you very much.